Okay, so today we're going to start chapter 36. This is the last chapter that we're going to be covering in this class, and then our final is already next Tuesday, so we only have a week until our final. Now, ideally, I would like it if there was a little bit more time in between when we cover new material and then when you actually get tested on it, but unfortunately, I don't set the final date, so our final's next Tuesday. So what I'm going to do to try to make it a little bit easier is I'm going to cover the two most important topics from chapter 36 today. And then it will be sort of a little bit more less important and supplementary material, and then also we'll just do X-ray diffraction on Thursday. So I'll save kind of the less important material for Thursday, and the two most important topics, single slit diffraction and diffraction gratings, we'll do today. So you have a little bit more time at least to process the most important things. And then I also want to go over the midterm because there were quite a few questions that I was surprised a lot of people got wrong because they were very important topics. So I want to make sure that I go over them and clear up any confusion since those are important topics that are likely to pop up on the final since it is cumulative. So we're going to go over a little bit of the midterm today, and then also just go over some basic study techniques for the class because I have been getting a lot of questions about that. So if you did great on the midterms and you don't need to go over the midterm or anything like that, you can just skip to when we start our chapter 36 material. But if you do want to go over the midterm and you do need some study techniques, obviously we will do that now. So the first thing that's most important is that most students don't believe me when I say this, but I will actually tell you what's on the exam. So when I say this is a very important topic or this is a very important type of question, that's because I plan on putting it on the exam. So listen to lectures. If you hear me say this is very important or this is a really important thing to understand and know, circle that, make a note of it in your notes. There's a good chance I will put that on the exam, or at least it's in the running for an exam question. So I do actually try to tell you what is going to be on the exam, so it's not like a surprise. So that being said, also, the most important thing you should do when you're studying is go over lecture problems and then discussion problems and then homework problems in that order. Because lecture problems are the most important, they're problems that I think like you absolutely should know how to do at the end of this introductory physics course. Physics is kind of all about concepts and solving problems, so they're problems that you absolutely should be able to solve by the end of the course. And I put them in lecture because I think that they're good problems. So make sure that you study lecture problems first, and I wouldn't even go on to studying discussion problems or homework problems or any other practice problems until you understand the lecture problems. Because I'm not going to put a question in lecture that I don't think is important to know. So the lecture problems are the number one most important problems to be able to solve. So if you do nothing but study lecture problems, for the final, you'll probably be in a better place than if you picked random questions out of the textbook to solve. So that's the number one thing. Once you're comfortable with lecture problems, then go on to discussion problems. And then once you're comfortable with discussion problems, then go on to homework problems, and then go on to, practice problems for mastering physics or whatever. And the other important thing is to go over the same problem multiple times, because what happens with a lot of people is you'll go over a problem once, be like, okay, I understand it, and then never look at it again because you understood it. And then it pops up on the exam, and now that 3 weeks have passed by since the last time you looked at it, you forget how to do it. So go over the same problem multiple times. Don't be scared to go over the same problem 3, 4, 5, 10 times. That's okay. When I was taking classes, there were problems that I would go over 15, 20 times, and sometimes I would just solve them all. I would solve it in a row over and over and over again, so that I developed like muscle memory of how to solve it, so that when I saw a question similar to it on an exam, I wouldn't even have to think about it. I would just immediately, like, my hand would just remember how to solve it. So it's really important to kind of like develop almost that muscle memory of how to solve physics problems. So don't be afraid to get a bunch of blank paper and just solve the same problem over and over and over again, because that's what helped me learn physics. And the other thing is, don't watch too many YouTube videos. Now, I don't mean don't watch too many cat YouTube videos or whatever. What I mean is don't watch too many like Khan Academy videos or whatever other channel you watch that has like physics videos that explain concepts. A lot of students kind of fall into the trap of thinking that if they just watch a lot of videos, like eventually it will click. But unfortunately, that doesn't usually happen. It's kind of like if you were trying to learn how to play the piano, you wouldn't expect to learn by just watching a lot of videos of other people playing the piano or someone explaining to you how to play the piano. You would have to sit down and actually like play the piano and practice. So it's the same thing with physics problems. You have to just sit down and practice. So if there's a technical, thing or a concept you don't understand, it's totally fine to watch a video about it, take notes, whatever. But don't fall into the trap of sitting there for like 3 hours watching Khan Academy videos and thinking that then you studied for 3 hours, because you didn't. So that's a very easy trap that a lot of students fall into. And now, in a similar vein to that is don't spend too much time reading the book either. Now, I know that might sound counterintuitive since it is our textbook, but both reading the book and watching videos are passive forms of studying. So what I mean by that is you're not actively doing work. Just like with the, learning how to play the piano, you can read a book about how to play the piano, but that's not going to teach you how to play the piano. You're not going to get any better. So you really need to sit down and just like actively solve problems in order to get better at solving physics problems. So just like watching YouTube videos can trick you into thinking you're studying when you're not, also reading the book can trick you into thinking you're studying when you're not. So there are obviously going to be some details that you should read in the book. You should outline the book. But what I would suggest is, outline it when there's a question that you don't really understand the topic behind it. Read that section in the book, outline it, get the main points out. But don't spend like 3-4 hours just reading the book. Now, if you read the book and outline it and do the derivations and go through the examples, that's different. But don't sit there and just passively read without actively doing problems and doing derivations as you read. Okay, so those all kind of go into the same vein of like you have to do active studying. So again, just think of it like you're trying to learn how to play an instrument. This also goes into cramming. You wouldn't really, if you had like a piano recital, you wouldn't try to learn everything the day before. And you wouldn't expect that would work either. So it also doesn't work with physics. You really have to practice every day, even if it's just a little bit, even if you just do one problem a day, just do one lecture problem a day, even just very quickly, just as long as you do a little bit every day, that's okay. Okay, so that's enough studying. So now let's go over some of the midterm questions. So the first one I want to go over is number 2. So that one, we had an electromagnetic wave traveling in the x direction, and it was polarized in the z direction. So that means our electric field, looked like that. It was polarized in the z direction. I want to know, in what direction is the magnetic field polarized? Now, a lot of people got this wrong, and I think what they did was just did x cross z to get the magnetic field, but that's not correct, right? Because remember, to find the direction of propagation was the electric field cross the B field. So E cross B gave you the direction of propagation. So you have to be very, very careful with that. As I said before, the cross product is not commutative, so it does matter what direction you take your cross product in. So here, our electric field, as we said, was in the K direction. We don't know what direction the magnetic field is in. And then the direction of propagation was in the X direction. So we'll call that the I hat direction. So you have to do K cross what is equal to I hat. So we can draw our little thingy here. And we have our little circle there. And so now we can see K cross, definitely not I, right? K cross J gives you I, but we're going backwards, so that introduces a negative sign. So K cross negative J gives you the positive I hat direction. So this here is actually negative I hat. oh, sorry, this was question 3, not question 2. So this was question 3. Now, question 2, I actually expected to be the easiest multiple choice question, but it was actually one of the ones that the most people got wrong. So I definitely want to go over that one because this is like a really important type of question to do with waves, since this is mostly like a waves class. So I think this problem, I think the fact that it was the magnetic field and it had a vector confused a lot of people. Now, if I had given you from like one of our earlier chapters on waves, if I had given you this equation and said, what direction is that wave traveling in? I feel like everybody would have gotten that right and said, well, it's traveling in the x direction, right? Because we said if you have kx minus omega t, it's traveling in the positive x direction. And if you have kx plus omega t, it's traveling in the negative x direction because, it has x right here. So I think the fact that the magnetic field has a vector confused a lot of people. And also maybe you thought that you needed to know the electric field or, something else since we had that extra vector. But, the magnetic field in that sense is just like a regular wave because the sign kz minus omega t tells you what direction the wave is traveling in because we just have z, so it's just traveling in the positive z direction, and that's it. So that was all you needed to do with that problem. I think a lot of people overthought it. So just keep that in mind. Sometimes, I try to make the multiple choice a little bit easier. So okay, so that those were the 2 multiple choice problems that most people got wrong. I was surprised how many people got right the polarization question because I actually thought that was going to be the trickiest problem, and then a lot of people got that right. So I was very pleased that most people got that one right. But let's just go over that. This is number 5. So let's just go over that a little bit quickly. So number 5, we had these 4 adjacent polarizers where each one was at an angle of 60 degrees. So it means like if this one was, perfectly straight like this next one was at 60 degrees from that, the next one was at another 60 degrees from that, and then this one was at another 60 degrees from that. Now, obviously, that adds up to, I guess, exactly 180. So then we have another 60 degrees. So this one, we had unpolarized light. So when we have unpolarized light here, we have I naught. And then we know that when unpolarized light travels through a polarization filter, no matter what angle that polarization filter's at, it's going to only let through half the light. So once it travels over this filter, we're at I naught over 2. And then once it now goes over the second filter, so now the light travels here, and it goes through the second filter, it's going to get that cosine squared term now, right? So now it's going to be the intensity that is going through the polarization filter, which is at I naught over 2, because that's the intensity of this light going through this filter. And then we're going to get a cosine squared times the angle of the polarization filter. So that's going to be a cosine squared 60. Then when it goes through this filter, so now your light is going through this filter, you're going to have the same thing, right? Where now this is the intensity of this light right here after it's gone through 2 polarization filters. And then you're just going to have that other cosine squared of 60. So you're going to get here another cosine squared 60. And then the same thing when you go through that final polarization filter, you're going to have another cosine squared 60. So your final answer will just be I over 2 times cosine squared 60, cosine squared 60, cosine squared 60, and that will be your final answer. And then I also tried to make this a little bit easier because cosine 60 is just 1/2. So you just have 1/2 squared, which is 1/4. So you just have 1/4 times 1/4 times 1/4, and then you just have 1/2 times that I over 2. And then you can just plug in to your calculator 2 times 4 times 4 times 4, instead of possibly making a mistake with all of these cosine squareds and everything here. And this just comes out to 1 over 128 I naught. So that's also a good thing to keep in mind, is that a lot of exams, not just mine, but a lot of even like textbook questions, so a lot of professors' exams will use either sine of 30 or cosine of 60 in the problem, because these are both just equal to 1/2, and that's really easy. So a lot of questions will use 30 or 60 degrees, depending on if you need cosine or sine, because it's so easy to remember that it's just equal to 1/2, then that makes your calculations a lot easier. So those numbers pop up a lot. So I would definitely make sure that you just memorize that, so that immediately when you see those, you can kind of just make these problems a little bit simpler for yourself. Okay, then I just want to go over some of the two short answer problems. So, was it number 6? No, number 7. I want to go over part of number 7. So for part B and C, you had this electromagnetic wave, standing wave, in a cavity. So it had 2 walls here, let's say. And it said that for the nth frequency, so whatever this frequency was, n, the nodes were spaced 2 centimeters apart. So, let's just say our wave looked something like that, where this is a node, this is a node, this is a node, and then this is a node, because we know for our electric field, at the surface of a conductor, our electric field is always 0, so the nodes are always at that surface of the conductor. And then, so they tell us that the nodes are spaced 2 centimeters apart. So we know this is 2, this is 2, this is 2, this is 2, right? 2 centimeters. And we also know that the nodes are every half wavelength, right? So this is obviously 1/2 wavelength, half wavelength, half wavelength, half wavelength. So what that tells us is that lambda over 2 is equal to 2 centimeters for this nth frequency, whatever that number n is. It's maybe the first frequency, second frequency. Here I drew the 1, 2, 3, fourth frequency, so I drew n is equal to 4 here. So whatever this is, half the wavelength is equal to 2 centimeters. Now for the next higher frequency, so for n plus 1, they tell us that now the spacing is 1.5 centimeters. So the wavelength is slightly shorter, because now you're fitting in more half wavelengths into that same that same cavity. So now we have lambda n plus 1 over 2 is equal to 1.5 centimeters. And now we want to know, well, how big is the cavity? So now what we can do is just take, let's just take the case, that first frequency, the nth frequency, and we know that we're going to be fitting an integer number of half wavelengths into that cavity, right? So this is just some integer, whatever the half wavelength is here, that's going to be equal to L. Then for the case of n plus 1, we're going to be fitting n plus 1 half wavelengths into that same length, right? The same cavity, L. So now what we have is we have 2 equations, and we can simplify this a little bit, because we know that in this case, in the case of the nth frequency, we know that lambda over 2 is equal to 2 centimeters, right? So I can just replace this with 2 centimeters. And then here, I know that lambda over 2, for the case of n plus 1, is equal to 1.5 centimeters. So I can just replace this with 1.5. And then what I can do is just rewrite my equations a little bit. So I have 2n is equal to L, and then 1.5 times n plus 1 is equal to L. And then all you have to do is just solve that system of equations for n and L, and you'll get that L is equal to 6 centimeters, and n is equal to 3, I think. Yeah. That's it. So there really wasn't that much work here. I know a lot of people thought that this was a lot more complicated than it really was, at least with the work portion of it. So also keep in mind that this one I took this part exactly from a lecture problem. I think it was example 6 in chapter 32, either part 1 or part 2. I think it was part 1. We went over this exact thing, just with different numbers. I think it was like 1.5 and 1.25 or something. But we went over this exact thing. So that's what I mean when I say make sure you do lecture problems, because if I'm going to give you a slightly more challenging problem, I want to give you one that I know you've seen already. So make sure you go over all the lecture problems, because a lot of people were caught off guard by this, but we had actually done it in lecture. So make sure you go over all the lecture problems for the final. Now, also keep in mind that number 6 was also almost exactly a discussion problem. Now, I made it a little bit trickier than the original discussion problem, but it was based on a discussion problem. I think about the first 2 parts, I think, were exactly from discussion. So yeah, make sure you go over lecture and discussion problems, obviously. Okay, and then just the last one I want to go over is that the lens and image problem. So for this one, it said that we had a lens, and to the left of the lens was some object. So we had our little object here. And then it said to the right of the object was an image on a screen. So now, since it told you that the image was on a screen, that means it has to be a real image, because only real images will, if you put like a screen there or a paper, will you see the actual image. Now, this is one of the cases where it's unfortunate that you're not actually in lab, because if you were in lab, you would actually be doing that and seeing that with a real image. You do see an image on a paper, and for virtual images, you don't see any image on any paper anywhere. So it's a little unfortunate you can't see this stuff in lab, but what are you gonna do? So you have now to the right of this image, to the right of the object, you have the image. Now you know that it's on the other side of the lens, because it says it's on a screen. So if it's on a screen, that means it's real. And the only type of lens that will form a real image is a converging lens. So you know that the object is on one side of the lens and the image has to be on the other side. So then we have our image over here. So this is our object and our image. And then they tell you that it's 2.5 times as big. So you know that the absolute value, at least, of the magnification is 2.5, right? But since we know that it's a converging lens, we know that, remember, the magnification is negative s over s prime. So since now we know that the image is to the right of the lens, we know that s prime is going to be positive. We also know that s is going to be positive. So that means that the image magnification has to be negative then, from this negative sign. So we know that m is actually negative 2.5 here. So it's inverted. And then they tell us that the image was 2.6 meters to the right of the object. So what does that tell us? Well, you might think that that's kind of useless, but we know that this distance is s, and we know that this distance is s prime. So if we know that this total distance gives us 2.6, then that means that we know that s plus s prime is going to give us 2.6. And now with these two equations, right, with this equation and this equation, so I'll rewrite that without the negative signs since they cancel out, we can solve for both s and s prime, and then we can solve for the focal length. So you really only had to get here. Getting here was the hard part, to get to these two equations. And then once you get there, it's kind of just algebra to solve for s and s prime, and then again algebra to solve for the focal length. So, right, so you solve for s and s prime here, and then just plug it into your 1 over s plus 1 over s prime is equal to 1 over the focal length problem. And that was really it. So again, this right here was just kind of the hardest part, and obviously where most people went wrong. So I would also recommend, when you're studying for the final, is go over the old midterm review videos, because like I said, same as with the questions in lecture, the problems that I do on the midterm review lectures are problems that I think you should know how to do. They're problems I think are good test problems. So that would be a great way to study for the final. Also, is to make sure you go over our midterm review problems and make sure you know how to do those problems, because something similar definitely could pop up on the final. I might use those problems, if not directly, at least as like inspiration for the final exam problems. Um, okay, so let's go on to today's material then. Okay, so like I said, today we're going to be doing diffraction. So we're going to be just looking at single slit diffraction and the diffraction grating. And then Thursday we're going to be doing X-ray diffraction, the intensity of the light on the diffraction, single slit diffraction, everything. So it's a little bit more supplementary. This is the real meat of chapter 36, is the two big equations we're going to see today. So in chapter 35, you saw that there are some, phenomena that can't be understood if you look at light solely as rays and use the geometric interpretation that we also did in chapter 34. So one of these phenomena is diffraction. And diffraction is basically just waves like flaring out around an edge. When you are in the next room from somebody and they say something, you can hear what they say because the sound waves diffract around the door or whatever it is. Now, we'll see on Thursday that the wavelength of the wave and the opening that it's diffracting like around or through sort of governs like how much things are diffracted. So we'll see that on Thursday. But basically, with light, you can look at this experiment sort of. And if you look at light purely as rays or even just as particles, if you have a little slit here and you shine light through it, you would expect that, the light ray just kind of comes out here and goes directly to that bright spot. But that's obviously not what happens. So you get what's called a diffraction pattern. So you get this like single big bright band in the middle, and then you get kind of these other little bands fading out. That's basically the wave just interfering with itself. So obviously in the dark bands is where it interferes destructively, and the bright bands is where it interferes constructively. So diffraction is just a type of interference. So okay, so that's basically just what diffraction is. Now there are two different types of diffraction. We're only going to be looking at the second type here. So the first type is called Fresnel diffraction. I know his name is French, so I'm not sure if I'm saying that correctly. But anyway, so Fresnel diffraction occurs when the source, screen, and obstacle are all very close together. So when I say that they're very close together, what that means is that you have this slit here, let's say, and let's say that the screen is very close to this this slit here where the light is coming from. It basically means that you can't approximate these rays as parallel when you like zoom in real close to where they're coming out of the slit here. So you can see that like this ray is almost perpendicular, and then this ray is like definitely not. So that means that this screen is too close to this for them to be considered parallel. Now, the other type of diffraction is called Fraunhofer diffraction, and that's where the screen and the diffraction slit are very far apart, so that it basically, when you zoom in, it essentially looks like these rays are all parallel. So that's what we want, because trying to derive or solve for these diffraction patterns where like the light spot, the dark spot, trying to solve for that without making that approximation is very hard. You have to then use Huygens principle, which we did, I forget in what chapter, but we did it a little bit. And like I said, you basically never use Huygens principle again. So in theory, you could use Huygens principle here, but it's like so like laborious and time consuming that the book doesn't use it either. To just say you can use Huygens principle to prove this, we're going to make an approximation and not use Huygens principle. So you really never use Huygens principle again. But if you wanted to, you could. So what you could do is look at each point along this this slit as a source for a new wave front. And then what you would do is like follow these little wave fronts out all the way to your screen and see where they interfere constructively and destructively, and then you could derive the bright and dark spot pattern. But like I said, that's like really, really time consuming, and making these approximations works very well, since we're almost always looking at cases where our screen and our diffraction slit are very far apart, so we can always use this type of diffraction and make the approximations that we're going to make today. So there is an interesting story with this Fresnel diffraction. So this I took out of the Halliday Resnick Walker book. So here, as I mentioned in some other lectures, there's kind of some back and forth throughout history about whether light was a particle or a wave. So, even up until the 1800s, so here we have 1819, most people thought that light was, a stream of particles. So our friend Fresnel here was an engineer, and he adhered to the wave theory of light. So he thought that light was a wave. So in 1819, the French Academy of Sciences had this basically like essay contest about diffraction. So Fresnel wrote one describing diffraction through the wave theory of light. Now, with this wave theory of light, you would get this very strange result. So what he predicted was basically that if you shine light, or you have a sphere in front of light, the diffraction pattern, as the waves flare around the edges of this sphere, they'll actually produce a bright spot in the center, which is completely opposite what you would expect if light was just rays or just particles. You'd expect them to just, go straight past the sphere, and directly behind the sphere it would be just dark, right? There'd be no bright spot behind the sphere. But if you use a wave theory of light, you can get this little bright spot behind the sphere where the waves sort of curl around the sphere and then interfere constructively. So Poisson pointed out that this would happen if Fresnel's theory of diffraction with light as a wave was correct. So what they decided to do was, well, let's test it, right? This is science, so we can test it. So they tested it, and it turned out that Fresnel was right, and that you did actually see this weird little bright spot behind basically in the shadow of a small sphere. So this is a good example of, science working the way it's supposed to. So, okay, let's move on. Okay, so now we're going to look at single slit diffraction and develop our equation for the dark spots. So what we're going to do here is we want to find an equation for the dark spots. Now we're going to talk on Thursday about why we're looking at the dark spots and not the light spots. But for now, we're just looking for the dark spots. We're going to develop an equation for them. So we have this slit here that's width A is the slit, and point P is a dark spot. So that means that these rays interfere destructively. So we have, let's redraw this. So we have this and this. And then we have this is like ray 1. And remember we said that the rays are basically far enough apart where we could treat them as parallel. So this is R1 and this is R2. Oops. So we're like super zoomed in on our light rays here so that they look parallel. And then what we're going to do is very similar to what we did in chapter 35. We're going to find the path length difference by drawing a line like this. So this is perpendicular to both rays here. And we want to find this path length difference between R1 and R2. So we're going to call this that should be R2 minus R1 is delta R. So that's going to be delta R that we're looking for. And then we have a little triangle here. So what we're going to do to find the first dark spot is we're actually going to cut the slit in two and look at a ray at the top of the slit and then a ray halfway down the slit. So this is our slit length A, where this part over here is A over 2, and this ray is coming from halfway in the slit. And then this angle here we're going to call theta. So this is basically the angle from the center of the slit to that first dark spot, on the screen over here. That's our angle theta. Now we can use some geometry to figure out some more of these angles so that we can figure out what this part is right here. So if this angle here is theta, we can see that this angle right here is also 90 degrees. So that means, right, because this is clearly a right angle here. So that means that this angle has to be 90 minus theta, right? Because we have theta, the whole thing is 90. So this angle in here has to be 90 minus theta. And then we have a triangle here. So if this is 90 minus theta, this is 90, this angle has to be theta as well. So this angle is actually also theta. So now what we can do is we can write, we have sine theta is opposite over hypotenuse, where the opposite side is this delta r, right? So that's delta r. And then the hypotenuse of our triangle is just, we said, a over 2, right? Because we're looking at halfway through the slit. So that's a over 2. Now we said we're looking for when the waves interfere destructively. So we know that they're going to interfere destructively when they're half a wavelength apart. So that means that delta r is going to be lambda over 2. So we're going to replace this with lambda over 2. So we can just rewrite this. We have a over 2 sine theta is equal to lambda over 2. So we can see that that will just simplify to a times sine theta is equal to lambda. So this is going to be the location of our first dark spot, where a is the slit width, theta is the angle from that center of the slit to the first dark spot. So it's, if our screen's over here, we'll look here. If our screen's over here, this is the angle theta. This is our first dark spot. Now we can find the location of the second dark spot by doing a similar thing, but instead of breaking this up into halves, we're actually going to break it up into quarters, because we want each pair of light rays essentially to cancel each other out. So what we're going to do here, same thing as I said before, but now we have 4 sections that we're breaking it up into. So we're going to do exactly the same thing, where we have, you're going to draw your triangle, but now you can see here, when we have that sine theta is equal to opposite over hypotenuse, the opposite side is still going to be lambda over 2, right? It's still the path difference, and since it's still destructive, we want it to be equal to 1/2 wavelength. So the opposite side, we still want to be lambda over 2, but now the hypotenuse of each of these triangles is a over 4, because we cut that into 4 pieces. We cut the slit into 4 pieces there. So now we can see that this we can give by a over 4 sine theta is equal to lambda over 2, which simplifies to a sine theta is equal to 2 lambda. So now this will give us the location of our second dark spot. So we can write this as a formula. And now again, I wouldn't worry too much about the derivation of these, because like I said, you have to technically use Huygens principle, which is just really not worth the effort. So it's really, this formula is what you should focus on. So this gives us the dark fringes. I'm going to show you a picture in a second. So this will give us the dark fringes where theta, as I said before, theta is the angle from that center point of our slit to the dark spot. So that's how we measure theta. So that's the angle theta there. That will give us the location of that dark spot. M is just the number of the dark spot. So it's either the first or second or third dark spot. Lambda is the wavelength of the light that we're using. A is the width of the slit. And theta I said already. So this is a picture of what it will look like. So this is we'll have a central bright spot when we shine light on a single slit, which makes sense because we kind of expected most of the light to go through that center part, and then at the edges it sort of interferes with itself. So we would expect kind of a center bright band, so we have that here. And then we have our first dark spot on each edge. So m is equal to 1 is just above that initial bright band. M is equal to -1 is below it, and then you just go up on either side. Now usually we don't really go beyond m is equal to 3 because the intensity gets so low, as we'll see on Thursday. The intensity fades off really fast. So usually in real life, you're not really working with m beyond like 3 really. Okay, so this is what the pattern will actually look like if you look through a diffraction grating, which again, unfortunately, you would really do in lab, but we can't. So a couple important things to note here. So you have to be careful because this equation that we just had, so this one right here, this obviously looks a lot like the equation that we saw in chapter 35, but now we're looking at the dark spots for a single slit, whereas in chapter 35 we had the same equation, but it was the bright spots on a double slit. So that's very important to remember, that basically what you're looking for, or what your equation represents for the single slit and the double slit, are basically opposites. So be really careful of that. This equation, like I said, gives the dark fringes for a single slit, not the bright fringes for a double slit. Then the other thing to be careful of is that m equals 0 doesn't correspond really to anything here, because m equals 0, would be in here somewhere, and that's a bright spot. So there's no dark spots at m is equal to 0. So it's very important to remember that our m starts at plus minus 1, and there's no 0 here. So m starts at plus minus 1, and it corresponds to our first dark spot after the central maximum, the central bright spot. Then also be careful that this angle theta is the angle from the center of the diffraction pattern to whatever dark fringe we're looking at, whether it's the first, second, or third. So as I said before here, if this is our dark spot, whatever it is, the second one in this case, this is the angle theta. So you look at the angle from the center of your slit to that dark spot. So that's the other important thing to remember here. Okay, so those are the important things you have to be careful for here. Now let's do an example with this. So here we have, we pass a 633 nanometer laser light through a small slit and observe the diffraction pattern on a screen 6 meters away. The distance on the screen between the centers of the first minima on either side of the central bright fringe is 32 millimeters. How wide is the slit? So that means you have your central, you got your central bright spot, and then you have your first dark spot on either side. The distance between the centers of those two dark spots is 32 millimeters. Then this is 6 meters apart, and we want to know what is the what is the width of the slit. So let's write down everything that we know first. We'll call x, so we know x is 6 meters, so that's the distance to the screen. We know that lambda is 633 nanometers. And we know that m is plus minus 1, right? Because we say it's the first dark fringe. So we know that m is plus minus 1. So what we're going to do here is actually use the small angle approximation. So remember we had a sine theta is equal to m lambda. So let's zoom in here a little bit, and let's write theta here. And then let's assume that this theta is very small. So remember that sine theta, the small angle approximation, sine theta is about equal to theta, but also tan theta is about equal to theta. So even though our equation has sine theta, since we're at a very small angle, we can actually use tan theta. And remember tan theta, so tangent is opposite over adjacent. So we can actually substitute where we see theta, we can substitute the opposite side over the adjacent side. So what we have here is we have, I guess they didn't really, let's draw this a little bit better. So let's draw this a little bit more carefully here. So this is the distance to our first dark fringe. So this is the angle theta that we're actually looking at. So that's our angle theta. So we can see there that we have, the opposite side from theta is the distance just from this midpoint here to the dark fringe. And then the adjacent side is just this distance, x. So we are going to call this ym. That's the distance from this center point here to the center of our dark fringe. We're going to call ym. So we can actually just replace this, and we're going to replace it with ym over x. So it's just the opposite side over the adjacent side. And then we want to know how wide is the slit. So we want to look for a. So let's just solve for a here. So we'll have xm lambda over ym. And so now we can start plugging things in. So x we said is 6 centimeters, right? 6, m we said is 1. It's the first dark fringe. Lambda we said is 633 nanometers. And then ym, we know the distance from dark fringe to dark fringe. So the distance ym is just going to be half that. So it will just be, ym will just be 32 over 2, which is 16. So this will actually just be 16 down here. And so this comes out to 2.4 times 10 to the negative 4 meters. So this is our answer here. And now this is an approximation that you can use anytime lambda is much smaller than the slit width. So, here we have like 600 nanometers, which is 10 to the negative 9, compared to something with 10 to the negative 4. So here our lambda is much smaller than our slit width, so this is an okay approximation to use. So we can use this anytime this condition holds. Okay, so now let's go into the other big topic from chapter 36. So that's the diffraction grating. So this one's very important. You'll see this pop up probably a lot, I'm sure, especially if you're an engineer. You'll probably see this a lot. So the diffraction grating is sort of the same as our single slit, but just like thousands of times. So we have a, grating with a bunch of little slits, all with the same width. So they all have this little width A here, and then they're spaced a distance D apart. So you have this slit is spaced a distance D from this slit, and then another distance D, another distance D, another distance D, another distance D. And you can have like many thousands of these slits in a diffraction grating. Typically, you'll have like a couple thousand per centimeter. So they're very, very small spacing with these diffraction gratings. And then basically you have your light go through each slit, and then you have a ray come out, or a wave front come out each slit, and then they'll again interfere constructively in some places and destructively in others. Now, we're not going to go through the derivation of the formula. Like I said, you have to use Huygens principle. It's just very not that instructive. So we'll just take the formula as a given. So the position, now we're looking at bright spots again. So you have to be very careful with that. When I write the formula sheet for the final, I'm not going to tell you if it's looking for a bright spot or a dark spot. So I would just give you this formula. So you have to know if it's a bright spot or a dark spot, depending on what type of grating it is, whether it's double slit, single slit, diffraction grating. So anyway, so the diffraction grating, we're looking for bright spots now. So it's the same idea, but now we have D here instead of A. So D is the distance between the slits. So as I said before, it's no longer the slit width we're looking at. It's now the distance between slits that we have. So we have this distance D between the slits. Sine theta, this angle theta is the same thing, where it's from the center of the grating to whatever bright spot we're looking at is that angle. M is just whatever number bright spot. And then lambda is the wavelength of the light. Okay, so let's just do some examples with this. Since we'll do some applications on Thursday and a little bit more of the concept and physics behind it we'll do on Thursday, but I want you guys to at least see these equations now, since these will be the ones that are more likely to pop up on the final on Tuesday. So I wanted to at least get a little bit more practice using these formulas today. So let's do two examples with this. So okay, so we have laser light of wavelength 632.8 nanometers passes through a diffraction grating. the first bright spot occurs at 17.8 plus minus from the central maximum. What is the line density? So that means the number of gratings, the number of lines per centimeter of this grating. And then we want to know how many additional bright spots are there. So what we can do to find the line densities, the lines per centimeter, is find D, so find the spacing between the slits, and then take its inverse, and that will give us the density. So let's just do that first. So we have d sine theta is equal to m lambda. So let's just find d first. So we have d is equal to m lambda over sine theta. So they say here that it's the first bright spot, so m is 1. Lambda is 632.8 nanometers. And then sine is 17.8 degrees. So we do this, plug that into your calculator, and you get 2.07 times 10 to the negative 6 meters. So that's the spacing between each line. So if we wanted to find the density, we would just have to take the inverse of that, because then it will give us the lines per meter, right? So if we just take the inverse of this, we would get units of per meter, which is what we want for the density. Okay, so here, actually they wanted us to find it in centimeters, so let's quickly just change this to centimeters. So 2.07 times 10 to the negative 6 meters is 2.07 times 10 to the negative 4 centimeters. So this will just be negative 4 centimeters here. So then just take the reciprocal of that, do 1 over 2.07 times 10 to the negative 4, and that will give you 4830. And now this is lines per centimeter. So this is now the density of our grating. So let's just add another page here. Okay, so that's the density. So then for the second part, we wanted to find how many additional bright spots are there beyond the first bright spots, and what angles do they occur at. So let's find where some more additional bright spots are. So we're going to have, again, d sine theta is m lambda. So we know where the first one is, so let's look for the second one. So let's do sine theta is equal to m lambda over d. Now, lambda over d is not going to be changing, right? Because the wavelength of the light is not changing, and the spacing of the gratings is not changing, but m is changing, right? Because we're looking for more bright spots. So I'm going to pull m out here and just do lambda over d. So let's just find what lambda over d is, since we know that that number isn't changing. So we had, it was 632.8 times 10 to the negative 9. We had 632 nanometers. And then d we said was 2.07 times 10 to the negative 6. So this comes out to 0.3057. So this number, like I said, is not changing because lambda over d doesn't change for our diffraction grating and our same light. So m, we did m is equal to 1 already. Now let's do m is equal to 2 and figure out what angle this second bright spot is at. So we'll have, let's do sine of theta 2 is equal to 2 times 0.3057. And then what we're going to want to do is obviously take sine inverse of that. So we're going to be doing theta 2 is equal to sine inverse of 2 times 0.3057. And that gives us 37.7. So theta 2, so that's the second bright spot, is going to happen at plus minus 37.7 degrees. Okay, so if you just measure from that central that central line and then take an angle of 37.7 degrees up. So you have an angle like this. And this is like our diffraction grating here. This is going to be our second bright spot. Now let's do m is equal to 3. So we'll do sine of theta 3 is 3 times 0.3057. So again, do sine inverse. So we have sine inverse of 3 times 0.3057. And that comes out to theta is plus minus 66.5 degrees. So now that means this angle here for our third bright spot would be 66.5, so it'd be, twice as big around here. And now, so that was m is equal to 3. And now, can we do m is equal to 4? Well, we know, as we said, that lambda over d is not changing. But if we tried m is equal to 4, and we know lambda over d is 0.3, we said, if I try 4 here, I'm going to get like 1.2 something, right? Because we have m times about 0.3. So that's going to give 1.2 something. But can I take sine inverse of 1.2? No, you can't take sine inverse of something greater than 1. So we don't have bright spots beyond m is equal to 3, right? Because we just can't do sine inverse of that. So what did it ask for exactly? It said, how many additional bright spots are there beyond the first bright spot? So that means we have 2 additional bright spots because we were able to calculate the angle for theta 2 and then theta 3, where m is 2 and m is 3. And then there's no more bright spots. And we found what angles they occur at. So that's what they mean by that. Eventually, you're going to get up to a point where you're doing sine inverse of something greater than 1, and that's obviously not possible. So that means you have no more bright spots. Okay, so now let's do another example with this diffraction grating. So here we have, if a diffraction grating produces a third order bright spot for red light, so the wavelength is 690 nanometers, at 65 degrees from the central maximum, at what angle will the second order bright spot be for violet light of wavelength 405 nanometers? And now when they say second order and third order, they just mean m is equal to 2 and m is equal to 3. So that's all the first, second, third order means. Okay, so let's just draw, just to draw a little picture of this, we have our diffraction grating here. It's saying we have a third order bright spot at 65 degrees up here with red light. And then we want to know at what angle will the second order bright spot for violet be. So I'm just I'll draw the second order one down here. So I want to know what angle is that for the violet light. So let's just write down everything we know. So we know m is equal to 3. For red light, we know 690 nanometers. And we know that theta is 65 degrees. So I'll call that 3r for the third red bright spot. And then we know for m is equal to 2, lambda we're looking for with 405 nanometer wavelength. And then we'll call that theta 2 violet, because it's the second order violet bright spot. And we want to know what that is. So now it's the same diffraction grating. So when we write d sine theta is equal to m lambda, for both of these cases, d is going to be the same, right? Because we're using the same diffraction grating, so obviously d can't change. But theta is going to change, obviously m is going to change, and lambda is going to change. Now, one thing you could do is take all of this information for the red light, plug that in here, and solve for d, and then do that same thing again. Now plug in d, m, lambda for the violet, and solve for theta. So you can do that, and that's totally fine. Or if you don't want to do all that solving, and you might introduce some extra errors with your calculator, you can kind of do it in just one step. So like I said, since we know that d is going to be the same for both, what we can do is sort of solve for d. So I'm going to write it like this. Okay, so I'm going to write it like this. And then I know that, as I said before, d will be will be the same for both of them. So what I can do is say, for the case of red light, 3 times lambda red light over sine theta third order red lambda theta is equal to 2 times the violet light divided by sine theta, where we're looking at the second order violet angle, because these are both equal to d, right? And I know d is the same for both of them. So I can just write my equation like this, and then all I have to do, I know lambda for both of them, I know this theta, and then all I have to do is solve for this theta here. So that's one way to do it. As I said before, you could do it the other way too, that's totally fine. So what I'll do here is I'll solve for theta lambda, so that gives me, I have sine theta 2v is equal to 2 lambda v over times sine theta 3r divided by 3 lambda red. So that gives me 2 times the wavelength for the violet light was 405 times 10 to the negative 9. And then I have sine of 65 for the third order red light here. And then I'm going to divide all this by 3 times the wavelength of red light, which is 690 nanometers. And then let me just add another page here. Okay, so what we had was sine of theta to violet was 2 times 3 times we had 405 divided by 690, because the nanometer is the 10 to the 9 canceled out for both. And then we had sine of theta, it was the third order red. Okay, and then, sorry, that was 65 degrees. 65? Yeah, 65. Okay, and then you just plug all that into your calculator, and you get that this is equal to 0.355. And then you can just take the sine inverse. So we have the sine inverse of 0.355, and then we get that this is equal to 20.7 degrees. So this is our answer here. So that means that this angle is 20.75, so it's obviously closer to the midpoint here than the third order red. So, you know, it looks like I drew it about okay. It's about right over here maybe. But okay, so that's where the second order bright spot for violet light would be, when we have a different lambda and a different m. Okay, so now we're just going to do one last problem here. So here we have the wavelengths of visible light range from 380 nanometers to about 750 nanometers. Find the angular limits of the first order visible spectrum produced by a plane grating, such as a diffraction grating, with 600 slits per millimeter when white light falls on the grating. Now, what that means, so remember that white light is made up of all of the colors. So we're going to have from purple, violet to red in there with the white light. Now, as we just saw in our previous example, that since red and violet light have different wavelengths, they're going to diffract differently. So in the full notes, so when I upload the slides, I'll include a picture of what I'm talking about. I forgot to include it here. But basically what you'll see, instead of just seeing a central maximum with like a couple of bright spots on either side, we'll actually see the central maximum with like rainbow colored bright spots on either side, because the red and violet light diffracts differently. So you'll actually see it separated out into like a rainbow when you see those other bright bands. So all they're saying here is that in that m is equal to 1 bright spot, so your first bright spot past the maximum, basically where is the violet and where is the red light? So what's like the angular spread there between the one that's like kind of diffracted the least and the one that's diffracted the most? So the first thing we want to do is find D, because here we're given the density, so we have 600 slits per millimeter, but we need to find the separation, which is D. And we know that if we just do 1 over 6,000 slits per millimeter, as we saw in our previous example, that will just give us d. So this comes out to 1.67 times 10 to the negative 6 meters. So that's our separation d. So if you're given either the density, so whenever you're given the density of the separation, you just take the reciprocal and you'll get the separation between the slits. So that's our d. Now we're going to be using obviously this equation. So we're going to have d sine theta is equal to m lambda. So I want to find the angular limits of the first order visible spectrum. So basically what we're going to do is plug in lambda is equal to 380 nanometers, where m is equal to 1, and then lambda is equal to 750 nanometers, where m is equal to 1 again, and see what theta is for both. So let's do violet first. So we're going to have, when we solve for, theta, it's going to look like this. So let's do that violet first. So violet, we'll call theta v, is going to be sine inverse of 1 times 380 times 10 to the negative 9 over 1.67 times 10 to the negative 6. And when you plug that into your calculator, this comes out to 13.2 degrees. So now we want to do the same thing for red light. So theta, this is red, so theta r, we'll have sine inverse of, again, 1 times 750 times 10 to the negative 9. D is the same. And then this comes out to, again, plug this into your calculator, and you will get 26.7 degrees. Oops. So this is the angular limits. So violet kind of diffracts the least, and it's only at 13.2 from that center here. It'll only be 13.2 degrees, and then red will diffract more, and it will be at 26.7 degrees. So again, I'll include a picture of this when I upload the slides, so you can kind of get a better visualization. And then for part B, we want to know, do the first and second order spectra overlap? So that means, since our red goes all the way out to 26.7, basically, does m is equal to 2 for violet start beyond that or start before that? So if we get 23, if we plug in the second order m is equal to 2 for violet light, does the angle, is it below 26.7 or is it above 26.7? So let's find the second order. So we'll do violet again. So we have theta, we'll call that 2, is sine inverse 2 times, it was 380 times 10 to the negative 9 divided by 1.67 times 10 to the negative 6 was the d. So this comes out to 27.1. So we can see here that this is bigger than the end point for that first bright spot on the red side here. So the first and second ones we can see already are not going to overlap. But let's just do the red diffraction just to be sure, even though we know that red's going to be greater than this. Let's just do the red to see. So for red, we'll have sine inverse of 2 times, this was 750 we were using, or 780, 750 I think, times 10 to the negative 9 over 1.67 times 10 to the negative 6. And this comes out to now 63.9 degrees. So now this one has an even bigger spread than our first one, where it goes from 27 to basically 64 degrees now. And then you can do the same thing for the second and third order, see if those overlap, and eventually you'll get to, as we did in our previous example, you'll get to a point where you're trying to take sine inverse of a number that's bigger than 1, which means you can't do that, and there are no more bright spots. So, okay, so this was a little bit more of a challenging example with the diffraction grating. We'll do, like I said, a little bit more supplementary stuff and the X-ray diffraction, which is important, on Thursday. But okay, so that's it for today, and I will see you guys next time.